It's my great honor to introduce Professor Cumrun Vafa at Harvard University. The title of his talk is String Theory and Homological Invariants for Three-manifolds.
Thank you. So thanks for introducing me. It's a great pleasure to be invited to give a talk here. As you can see, we have made a switch from mathematics to physics, going from backward to the top. Hopefully that won't distract too much. So I'm going to talk about some work I've done recently past year or so with Sergei Gukov and Pavel Petrov, as well as with today. And these are based on these.
I think your mic is. Thank you.
So I tried to came red. Thank you. So it's based on these two papers. So let me explain the plan for the talk. First of all, I review the connection between knot homology and physics. This is old work, roughly like 15-year-old or maybe more than that work, and connected to more modern ways of thinking about it. And then I talk about more recent work, which is the connection of that replacing the knot here with the three-manifold piece. So trying to say what you do for the homology when you want to replace knots with three-manifold itself. And then I give some examples, and then I talk about some extensions. So that's the plan for my talk. So I will first start with the physical setup for knot homology. So in the physics context, we think of it in this following way. We start from a six-dimensional object. So in string theory, we have these interesting objects which arose, which we call branes, but you can think about this as something in 6 dimensions, some structure in 6 dimensions, some standalone theory in 6 dimensions, and you can use it as a gadget to get new stuff. That's the way we use it in physics. So the gadget that we have is 6-dimensional, and we want to use it to get 3-dimensional invariants. That's the basic mathematical picture you should have in mind. How out of 6 dimensions you're going to get 3-dimensional invariants. So these 6-dimensional gadgets, or in these called M5 branes, that's just the word, they're 6-dimensional theories. They live in 6 dimensions, and they're classified by ADE, the familiar simply laced Lie groups, ADE. So there's one-to-one correspondence between ADE and these choices. So you choose ADE group, you have chosen one of these 60 theories. And the object we are going to, for the knot homology, the object we start with, the 6-dimensional geometry topology is extremely simple. We just take basically 3-dimensional space times 3 sphere, R3, just flat R3 times a 3-dimensional sphere. The geometry looks very boring, in fact. And the only thing we are choosing is which one of these ADs we are choosing. You choose one of them, let's say. Now, more precisely, the way it appears in string theory is that this S3 is part of a Calabi-Yau. So in fact, it's part of the cotangent of S3. So it's the zero section of this. And this R3 is part of our space-time, which is part of what we don't compactify in string theory. And then, so this is part of the underlying manifold. And then we want to introduce a knot. So what we do, we take a knot inside S3. And then we viewing this as a Lagrangian and constructing a conormal bundle construction, we can introduce a Lagrangian, which intersects S3 on this knot. And then we wrap, again, we consider these to have two different stacks of what we call M5 branes. So some subspace involving S3 times R3, another subspace wrapped around this new Lagrangian times R3. So we have two stacks of these 6-dimensional objects, one stacked differently. And this is the setup that we studied with Hiroshi Oguri. This is about, I think it was in 1999, so it's a long time ago by now. So using this setup, we consider the resulting it results for us to Hilbert space. In the physical setup, we study particles, good kind of particles or ground states of some quantum mechanics. And we studied, we related the Chern-Simon invariants by studying spins of these particles. Basically, by studying what kind of spins we get, we managed to recover the Chern-Simon knot invariance. So this is basically a Hilbert space reformulation of Chern-Simon invariance. Now, more generally, there's an extra gradation, the R symmetry in this Hilbert space, that can be used to define a refinement of this. And this is something that we studied a while back with Gukov and Schwartz. And in certain cases, it can be related to a refined version of Chern-Simons, as was shown by Aganagich and Shakirov. And later, using string dualities, these states, counting of these states and these invariants can be reformulated, as Witten did, to counting certain solutions in gauge theories. So all these formulations are basically coming from this six-dimensional gadget involving an ADE six-dimensional theory. So you start with a knot, you study the Hilbert space, the ground state of the BPS states, and there are two integers which characterize what states you get. The Humphrey polynomial arises by taking an index traced over the states in the Hilbert space with some gradation of one of them. And this gives you a Humphrey polynomial associated with this K with some Q, which in this case Q is related to the Chern-Simon level. And then you can do the analog of the Poincare polynomial if you wish, just by summing over all states in some way. And the index that one computes as Humphrey is just the particular specialization of the Poincare. For special knots, such as torus knots, we end up with extra symmetries leading to additional gradation. So the Hilbert space that we end up with doesn't have just two gradations, has an extra gradation. And in these cases, it turns out that for very special cases that we have one studies quite actually frequently, you end up getting a situation where the Hilbert space has locking of the gradations, that the dimension of the Hilbert space for the R2 not equal to R3 is empty, so you only have R2 equals to R3. So you can reformulate the Poincare polynomial again as an index-like computation by doing sum over the third gradation. So you have this refinement, which can also be viewed as an index in this context. So the Poincare polynomial can be viewed as like an Euler characteristic again, where you can actually view this extra gradation as a way to get to it. So this was, and there's of course the mathematical work kind of in parallel by Chovanov and Rozhansky, which starts again more or less around the same time period, which completely different, develops the similar kind of things, and that's still developing. So it's completely different ideas, and there are some relations between them, and one can check the ideas kind of match. But I don't want to talk about the relation so much. Instead, I want to come to the issue having to do with three manifolds. So this was kind of the setup for the not invariants, and you want to go to, okay, so what can you say about three manifolds and the invariants for them? Is there homological three invariants for three manifolds? So the same thing. We don't have to do anything new. We just take the 60 theory, the same 60 theory. Now, instead of the boring three-sphere, we just choose a non-trivial manifold, three-manifold X. Okay, so that's not a brilliant idea. It's just kind of an obvious thing to do. So you just take the three-manifold X and just study the resulting theory. So the question is, what about this resulting theory is going to be related to what you know about the three-manifold invariants? For example, we know there is this Witten-Reshetikhin-Torayev invariance for three manifolds. How can you recover that from an information having to do with this six-dimensional theory on these three manifolds? Can you recover them? Are there other invariants? Is there a refinement for the WRT? Is there a homological version of this which gives you a refinement? So in order to see how these kind of arise, I have learned my lesson when I give a math talk, state the results. And if that's all you say, that's fine. But you definitely have to state the results. So I'm going to state the results first. So this is basically the statement of what we claim is going to arise in the physics context. And then I'll try to explain how they kind of arise from the physics. So the statement is this. Let me, for simplicity, this is not necessary really, but it simplifies my formulas. So let's, for simplicity, assume we are talking about the rational homology three spheres. So the B1 of the manifold is 0. And consider these homomorphisms from H1 of X with integer coefficients to the Cartan of AD modulo the while of AD. So you can think about this as abelian flat connections, if you wish, with the ADE group. So you can study these. So it's kind of an abelian flat connections in X. And you look at C. So you can think about this C as a Cartan torus and the W as the Y group. So there's this extra data we have introduced, choice of this abelian flat connection. So for each three-manifold X and each class of abelian flat connection A, we get homological invariant. So you associate with three-manifold A with double gradations. Just like the case of knots. So just like the case of knots, in the case of knots, we didn't have, we had instead of X was boring, you had a knot. There was no notion of this flat connection, but you have something analogous to these guys. And you have, in this context, you can look at the analog of the Poincare polynomial, if you wish, just like we did for the knots. Now, in this case, it depends on the choice of the abelian flat connection. A mathematically more precise definition we can try to give it is the following form. You can consider the complexified gauge connection on X of the ADE type. And there's a natural gradient flow on this space using the Chern-Simon action on it. And for each flat connection A, there is a Lagrangian subspace of A, which you can think about it as using the Lifshitz symbol associated with the gradient flow here. And this is the kind of a construction that Witten was using in the context of knots, invariants. And then you can start counting the following set of solutions, where you look at a set of solutions where you have one variable, and the gauge connection on one end, so there's a function on one variable, one extra direction, x. And as x goes to 0, you have a connection which reduces to having a pole structure. This is what's called a non-pole structure, where these TA denote the embedding, the principal embedding of the Lie algebra of SU to the Lie algebra of the group G. And these E mu A can be viewed as the Wehrbein defining your metric on the three-manifold. So there's some reduction that you're looking for. You're looking for the solutions on one end, going in this way in terms of poles. And on the other end, they go to the corresponding flat connections you want, and using the gradient flow structure. So you want to have on one end go like this, and on the other one going like that, with a gradient flow. And from this pole data, together with the index of the instanton and the R2 charge, defines for you the corresponding Hilbert space. So you're counting such solutions. So that's morally what it is. To make this precise, of course, takes some work. But the idea is that you have some object which is double labeled. One of them, the pole data is fixed, and the other one is the abelian data structure is fixed. And you count solutions where there are two integers. One is counting the instanton number, and the other one is counting the R charge in this system. So that's roughly the piece that one can try to make precise, but that's something I'm not going to try to do. Then you can consider an object which is the unrefined case, where you're specializing the corresponding Poincare polynomial for this case, where it reduces t equals to 1. So this will give you an object which depends on an abelian flat connection with a parameter q. It's roughly speaking, not exactly, roughly speaking, it's the partition function of Chern-Simon near the flat A connection, where q should be viewed as the parameter which defines the Chern-Simon coupling constant. And it turns out that the Witten-Rishtikin-Turaev invariants can be recast as a linear combination of these z's, with something which looks complicated here. I can describe one by one with the R, but they're just some fixed integers, some fixed expressions in terms of the group and the linking product, which is defined in terms of the H1 of the manifold, which is mapped to the Q mod Z, combined with the killing form, so define some kind of inner product, which recasts the formula as a linear combination of these guys. So basically, it's like a Fourier transform with the specific coefficients. You sum them up, and you're supposed to be getting the Witten-Rishtikin-Turaev invariants out of those. So now, in this way, we have a refinement of the Witten-Rishtikin-Turaev, because first of all, we have these objects. Secondly, this came about by a specialization. So there's more information that we have. And so you could also in this way define the refined version of the Chern-Simon, which you don't specialize, and you have a similar formula in that context, where you just take the linear combination of these z's and you get what would be the refined Chern-Simon's theory. Again, this would make sense in the particular cases where you have extra symmetries, where it allows you to do this kind of index-like computations. So this is the basic general setup. So the basic general setup is that we are associating to three-manifold X with abelian flat connections of AD type, a Hilbert space, which we believe is the invariant of it, with double gradation. So that's the physics statement. Any questions about it?
Is there expected to have any modular property of these generating series in some lineage?
There are some things which have to do with there are some kind of symmetries. This, for example, this matrix has to do with what we call the S-duality matrix. So there's some kind of a Fourier transform involving the SL2s U of n equals to 4 Yang-Mills. But per se, it's just a Hilbert space. For each one of them, there's nothing, no structure per se. So as I just said, these are just, you can view these as motivations. From mathematics side, you can say, okay, so physicists are telling us there are these things. Let's see, figure out what could they be. That could be your way of thinking about it, come up with ways to see it or connect it to things known. I will later on mention some connection of these with Seiberg-Witten floor homologies. So these do connect to that, and I will explain the connection later. So this could be viewed as a connection with that. I will tell you later. Yeah. So the story is quite general. So let me start. So that was the statement. Now I will say what is the physics? How do we get to these kind of things from this? So we consider, so there's these magical 6-dimensional gadgets, these 6-dimensional theories. Instead of taking S3, we take X. That's what we do. But the rest of the space is R3. So you take 6D, you put it on something, and you get some theory in R3. Now, just before I go on to this, I want to say that this is directly also related to the Langland, geometric Langland program realized in the physics context, namely, in that context, this X will be a 4-manifold, and this R3 will be replaced by 2 torus. And the Lang-Lang duality is related to the fact that the torus has, choice of A and B cycles. It's a very simple statement. So my point here is that this 60 gadgets should be taken very seriously, and different kinds of pieces of math would emerge from different kinds of questions you might ask. So you go back, anyhow, so let me go back down here. So one thing you could do is you take a 3-manifold, and you take it, shrink it to small size. You take the metric and shrink it. So you just get effectively only a 3-dimensional manifold left over because you have shrunk one side. So you get an effective theory in R3. And so this theory, in the limit where you shrink that X to be X very, very small, should be a super conformal field theory. In other words, there's no scale left. You have shrunk everything to 0 size. You would expect to be what's called a super conformal field theory. And in many cases, the resulting theory can be effectively described in terms of low energy limit of a quiver gauge theory. So in some cases, you give me a manifold X, and I can produce for you what is that leftover theory. But in general, the fact that you will get a theory is just based on physical principle. We expect that to happen. So in special cases, some examples has been worked out, beginning with the work by Dimofti, Gayotto, and Gukov. The theory, the superconformal theory, has a superconformal symmetry given by this group, supergroup, OSP4/2. So superconformal groups have symmetry based on a supergroup. The bosonic part of this group is just SO3, which is some version of SP4, times SO2. So you can think of these as the non-fermionic parts of this supergroup. This has 3 independent Cartans, so 2 from here and 1 from there. So it's rank 3. So naively, every element of the Hilbert space, since this is a symmetry, every element of the Hilbert space will come with 3 gradations, depending on these 3 charges. So we get a map. You start with an X. You get a superconformal field theory X in 3 dimensions. This 3 dimension is R3, the 3 dimensional of R3. Of course, 3 plus 3 is 6. So these 3, and this is 3-dimensional, and this is 3-dimensional because they add up to 6. And this 2 denotes the fact that you have a certain number of supersymmetry, n equal to 2 supersymmetry. Now, not only does this give you a Hilbert space, but it gives you a huge amount of data. In other words, there's a Hilbert space, there's operators, there's a product between them. So there's a huge amount of data that you don't want to know. It's too much. Okay? You want to extract from it the invariants associated with 3 manifolds. You don't want the whole data. So the question is, what is a nice subspace? What is a nice question in this context, which could be viewed as a simple or a nice way to think about the invariance for three manifolds. So to describe the resulting Hilbert space, we view the space-time. So the R3 was the leftover space. We view it as a one-dimensional time times a two-dimensional space. So space and time, you physically think of as time and space. And two-dimensional space, by adding a point at infinity, can be viewed, which is conformally equivalent to the two-sphere. So sometimes we view this R2 with the one-point compactification as a two-sphere. And that's a very convenient case for the case of superconformal field theories. So we kind of view our space as S2 instead of R2, and a time which can be taken to be R, or sometimes we identify it to make it a circle. To compute a partition function of this theory, we can include gradations associated with the three cartans of the superconformal group, which is the bosonic parts of it, is this, as I mentioned before. So there are three cartans you can introduce. And you can take a trace over the Hilbert space with some gradation. So this gives you the spectrum or degeneracy of these Hilbert spaces with the particular gradations. So you can view this as a partition function where you take a product of S1 times S2. But as you go around S1, before taking a trace means completing this time to a circle. But before taking the trace, you do some appropriate rotations or some identification of the fields as you go along. So for example, one of these Qs might involve rotating the two-sphere as you go around the S1. So it's not strictly a product, but some twisted product as you go around the S1. So depending on what Qs you put, this partition function, computation of the partition function of this three-dimensional space will give you this partition function, which depends on these three variables. This is still too complicated to compute. It's not easy to compute. And in fact, it might depend on the choices of the metric on X. So it's not quite an invariant yet. You don't want it to depend on the details on X. So for it to not depend on it, it turns out that you focus on the ground states, which are these states that are preserved by some supersymmetry. So the BPS states. So you look at some supercharge, you look at the subspace, and you look at those cases that would be kind of protected based on deformations. And so you look at, for example, the partition function, which is a trace of -1 to the F, Q to the S, where S is some kind of a spin. So you can do this analog of ground state, which is protected, and then you can still have some gradation, which is consistent with that protection, and you can compute objects like that. So in fact, if you take, this is very much like the usual cohomology story. There's a D and a D dagger, or Q a Q dagger. Their commutator gives you some combination, linear combination of these cartans, these three cartans. So for the ground states, one linear combination vanishes, just because the right-hand side should vanish. So for that combination to vanish means that out of the three gradation, one of them is fixed in terms of the other two. So there are two independent gradations for the ground state. So the superconformal symmetry automatically tells you that you only have two natural gradations. So this is just from physics, without doing anything. You already know, OK, I should be asking about doubly graded Hilbert space. This is just symmetry principle, nothing fancy. So from the physics side, just the symmetries of the problem tell you should be looking for a Hilbert space with two gradations as object which is protected by supersymmetry. OK, so if you just took the index, then you would just get the analog very much like what we had as the Euler characteristic of this complex, if you wish. But just like the Poincare polynomial, you have more information. There's more in the cohomology. And you can count all the states in the Hilbert space. And those will give you the double gradation as we had before. So this is the double gradations that we talked with before. So this is very similar to the case of the knots that we mentioned before. It almost repeats that. Just in the case of the knots and the links, for some specific knots with extra symmetries, it turns out sometimes you have extra flavor symmetry. And then there's a locking, it turns out, between the charges that was one of these R symmetries with the corresponding flavor symmetry. And you can then reformulate the partition function or the Poincare polynomial still in terms of some kind of an index computation. But not always. This is only in some cases. But nevertheless, the general case, you always will have a Hilbert space with double gradation. And that's what the physics already predicts. So so this is already a new invariant. What I just told you, the Hilbert space with double gradation is a new invariant. And the reason I'm not going to focus on that is that this can be refined, that this can be decomposed into pieces, each of which can be connected to the unrefined version of which can be connected to WRT invariants. Otherwise, this is already could be the end of the story. We just defined an invariant, and it doesn't depend even on a flat abelian connection or anything like that. So in other words, it's neater. Just depends on the three-manifold. You give me a three-manifold, I'll give you, and choose an ADE, three-manifold, choice of an ADE, I give you a Hilbert space with double gradation, which is homological invariant for that three-manifold. That is it. So that's already a concrete statement. The next statement could be, okay, what does it have to do with the things that I'm familiar with in the context of WRT? Let me Chern-Simon partition functions. Are there other versions? How do you think about those cases then? To get those, you have to do something which looks a little uglier from the kind of geometry that we did. So we said, start from a two-sphere, but it turns out to be natural to elongate, take the limit in which the S2 is kind of elongated to basically two cigars and cut in the middle. So it turns out to be natural to do this, thinking about the S2 as being glued of two pieces of cigar. And so therefore, you want to study basically each half at a time and glue them together. So you try to decompose the problem to the product problem of this one and that side. Once you do that, the Hilbert space kind of decomposes to two pieces. The Hilbert space on the left and the right basically repeated because they're more or less the same space by some symmetry, except you need to specify boundary conditions because what goes in the middle? So roughly speaking, you expect the H to be a sum of tensor products of the Hilbert space with something in the middle. So the relevant part of the story from the physics seems to be related to A being related to the abelian flat connections in the middle. And these are the objects we're going to be using. Each half of this is what we're going to be using to get new invariants, which are going to be related to our to the WRT, refinement of WRT. So if you study with the six-dimensional theory, which is the 2-0 theory with the A type, let's say A type means a SUN type, on X times S1 times cigar, where as you go around S1, you rotate this cigar by the parameter Q, we see that we will show that from this setup, you're going to get the topological string on, there's an argument why you get topological string here on X. So in other words, this is another argument that you can roughly see why we should be getting the WRT invariance. It is well known, so let me say it a little more clearly. It is well known in the context of Gromov-Witten invariance, when you have open strings, that computing a Lagrangian inside the Calabi-Yau gives you Chern-Simons theory. Okay? Well, think about X as part of Calabi-Yau, and this is the leftover space. It turns out the Chern-Simons theory that you get involves this S1 times the cigar with a half twist. So therefore, this is the usual statement that the Gromov-Witten gives you Chern-Simon theory. So the fact that you would get the WRT invariance is part of the package of the relation between the six-dimensional theory and topological string, the Gromov-Witten invariance. Okay, so this kind of connects with part of what Melissa was discussing in the last talk. So that same open string that she was talking about packages into Chern-Simons theory, and in this unrefined case, you'll get that object. Except you have to be a bit careful because you have to talk about what boundary conditions you put here. So this is morally correct, but you have to say exactly what you mean by this relation because there's some boundary condition data on this cigar you need to specify. So the statement would be that the Hilbert space, if you look at the doubled object, it's roughly speaking the product of, if you want to refine it, you have a function of Q and T. It's a double function of these guys, the partition function, which follows the existence of the Hilbert space decomposition. Computing the corresponding partition function, you get such a structure. The Q and T get inverted for the other half of the cigar. So one cigar gives QT, the other one gives Q inverse T inverse. And these objects can be viewed as the Poincare polynomials associated with the Hilbert space on half of the cigar. And from this data, you can obtain, as I mentioned, by doing that sum that I wrote, the Chern-Simons partition functions, the unrefined ones when you put T equals to 1. Now, to actually use this, to actually say something about this concretely, you have to have a handle on these 2, 0 theories on the corresponding X manifold. And in many cases, given a manifold, we can actually write the corresponding three-dimensional effective theory as a quiver theory. So then another piece of math comes in. You study representations of quiver, and using that theory of quiver and representation and so forth, you can actually compute the partition function directly. So these functions you can actually compute using yet another machinery on this leftover three-manifold. So in other words, you start with the 6D theory, you're interested in X, you translated the problem of putting the six-manifold on X to some other theory in 3D, which gives a quiver description whose representations can be realized, and you can write the generating function for the representations. That gives you the partition functions for us, which is the objects I was telling you about. So they directly maps to the kind of objects that one would be interested in computing. So let me just give you an example. Lens space, so that you get a flavor of what it is, what kind of objects you get. So the lens space, so in other words, we take the X to be S3 mod ZP, the LP1. And the corresponding 3D theory turns out to be the quiver gauge theory with SUN with some adjoint field. So this is a UN Chern-Simons, some adjoint field, and the P of the lens space gets related to the level of the Chern-Simons. Now, I hope it's not confusing. The three-dimensional theory that we are talking about on R3 is three-dimensional. So there's another Chern-Simon. So don't confuse this Chern-Simon with the Chern-Simons on X. This is Chern-Simons on the other three dimensions. 3 plus 3 is a 6, so you have to be careful which three-dimensional we're talking about. So it's the three-dimensional of the leftover space. There's a supersymmetric Chern-Simons, UN gauge group, level P that we're talking about. This is level of the Chern-Simons theory with an extra adjoint field. This T denotes the fact that this adjoint field has a charge T. That's the extra gradation I was telling you about. So the extra gradation corresponds to the rotation of this extra adjoint scalar in this theory. So if you introduce this Pochhammer symbol, which is this infinite product, and it goes to 0 to infinity of this 1 minus q to the n, the partition function of this theory can be written in terms of the products of these Pochhammer symbols with some integral you need to do over the z, and this will give you a function of q at the end. The main point I'm trying to make is that this is very explicit. You can write it as an infinite product and all that, but it's not complicated. And there's some contour prescription you can actually integrate and compute using suitable residues of this partition function as a function of q. So there's some explicit formula. So now this is a complicated formula, so I want to give you a feeling about what it looks like for a very simple case, namely p equals to 1, S3. So just take a very simple case. If you take S3, and if you do the computation, so let's go back to the refined case, which have one extra parameter. You can do the same thing. We only have one block, and the partition function we get is this object. So this is Z0 is a product from I equals to 1 to n for the UN thing. With this infinite product in this form, where here in the denominator you have a product from I equals to 1 to n. In the limit as t goes to 1, this is the undefined case, you get this formula. This formula, for people who are experts on Chern-Simons theory of SUN, will recognize this as a partition function of SUN Chern-Simons on S3 up to some overall normalization factor. So this is a simple polynomial product of some certain signs. And this is, in fact, related to the WRT for S3. But you see the WRT for S3 is coming from its infinite product in this structure. So it's much more structure. Here it gets canceled when you put t equals to 1. So the structure simplifies dramatically in the undefined limit to give you this, in some sense, boring-looking answer compared to that infinite product. So the refined version of the Hilbert space is far more intricate. The space is much more intricate and seems to carry much more structure to it. So this is kind of the basic kind of ingredient setup. That is, you have some kind of a theory in 6D. You put it on the manifold. You study the Hilbert space. It will tell you the gadgets you have. If you can formulate that three-dimensional theory simple enough, you can compute everything in it. And the refined version for the lens space, this was just for S3, but if you do the lens space, you get some formulas, which again depends on Q and T, and you get some kind of a formula which is manageable. It's not that complicated. So here you have some kind of a contours again by more variables, but that's about it. So anyhow, I just want to say that this is the theta function, and this is some Pochhammer symbols. The main point here is that it's computable. I don't want to say more than that. The statement is that it's not that complicated to write down, and it's one can, in principle, compute these. So what are the possible extensions here? Well, one possible extension is that you can include nuts. That's not surprising because already nuts was the same setup. We had M5 branes. We can include other M5 branes intersecting M5 branes. So you can easily include nuts. You can include nuts in two ways. One is using knot complements, take a three-manifold and study it that way, or the usual way where you put extra M5 brane intersecting this other 5 brane. So that's one way. You can also connect it to Seiberg-Witten Floor homology, but in the following way. If you take, you can extend this story to UN/M. So here I was talking about the ADE case, but you can actually extend it to supergroup case. So you can have a UN/M version, and the case n equals to m equals to 1 turns out to be equivalent, we believe, to the Seiberg-Witten Floor homology. And let me, perhaps I should explain that with a picture. So the geometry that we had started was S1 times a cigar. And in the case, so we put n M5 branes here. But in the case of the Seiberg-Witten geometry, it turns out instead of taking S1 times a cigar, you take S1 times a pinch cylinder. So now it's 2 cigars, touching like that. A singular geometry like this. This is the part of the Seiberg-Witten curve, which is xy equals 0. So you can think about these pinched cylinder as xy equal to 0, which is precisely the Seiberg-Witten curve at the point where you talk about the monopole equations. So the monopole equations arises in this context as S1 times the pinch cigar. And you can show that if you put NM5 branes here and MM5 branes here, you get the UN/M theory. But if you just take a single one, which is the case for Seiberg-Witten, so Seiberg-Witten theory can be reformulated as a pinch cigar times S1 times the 3-manifold. So here, this is again adds up to this geometry. So I guess I call this here X. This geometry is 6-dimensional, 2-dimensional in this pinch cylinder, a circle, and a 3-manifold. So here I reverse that and put X upstairs, and then you have a 3-dimensional left over. And it's known that the M5 brane on a cylinder gives you the monopole equation. That's the Seiberg-Witten geometry in terms of M5 brane. So M5 brane has a lot of uses. It gives you Seiberg-Witten equation. It gives you the 3-manifold invariants. It's giving you the Lang program and all that. So they're all related, and I'm explaining to you how the Seiberg-Witten story will arise here. And the fact that you have 1 and 1 here, you get U1/1 as part of the homological one. And in this case, also it's known that in the context of Seiberg-Witten floor homology, you need a spin C structure. So there's an extra data, and that maps to the flat abelian connection that I was talking about. So there's an extra data needed also to define the manifold invariant, and that matches the same thing I was telling you about here. So, sorry. So that's this one, the N/M one. Now, you could say, OK, so that's great. You have a 6-dimensional gadget, and you get us this stuff. Do you have any other 6-dimensional gadget? And it turns out the answer is yes. We have 2 different classes of 6-dimensional gadgets, and that's it. One class of 6-dimensional gadgets is this 2,0 theory, the M5 brane, which has been studied extensively in physics, and also it's being applied, as we can see, to the math context. But there is another one, which is half as much supersymmetry. And this is the 1,0 theories, 6-dimensional 1,0 theories. And it turns out that these, instead of AD, they are classified by singularities of elliptic 3-folds. So in fact, you can think about the 2,0 theories. In some sense, they are classified by elliptic singularities of 2-folds, of Calabi 2-folds. That's AD, kind of. And this is the 3-fold version. So if you take the 3-fold version, those singularities label these other classes. And then you can do the same kind of game we just did for this class and see what kind of new invariants you get for 3 manifolds. Everything you do, you can now repeat. So these could clearly, so if you did that, this could lead, instead of three-dimensional theories with n equal to 2 supersymmetry, you have to reduce the number of supersymmetry by half, so you should get 3D theories with n equals to 1 supersymmetry. And this could lead to homological invariance with a single gradient, because now you have one less symmetry. You lose one gradation, so you seem to lose a double gradation and just get one gradation, so that seems like going backwards, except you go forward because there's a huge number of elliptic threefold singularities. And so you can now have a bigger set of gadgets you can apply with a smaller gradation for each one, and could carry inequivalent information for the invariance in particular. The classification of these elliptic threefold singularities has recently been done in physics literature by some works we did and some other people did. And this actually gives you a beautiful generalization of ADE. So it turns out to be characterized by Dynkin-like diagrams, so basically trees, with each node as self-intersection not just being -2, but running from -2 all the way to -12 with some very specific rules of how those intersections arise. And these come from the blow-up of the geometry of the base of the elliptic threefold fibration. So it gives you some data about what can happen, and that has been studied. So for each one of those, you can take this gadget and apply it to this setup. And then the index version of them. So there's a single gradation, and you can say, you can either do the Poincaré polynomial for it or the index version. If you take the index version, you get something similar to the Rozhansky-Witten story. So the Rozhansky-Witten studied the analog of the 3D sig models with target space and hyperkähler three-manifolds. That has the same amount of supersymmetry as I'm now talking about. So this picture will unify this as part of the other story. So if you view the 60 theories as the guiding principle of what you can do, you'll get both extension of what would be the Rozhansky-Witten theory as well as the refined version of this Chern-Simon all in one package. So you can have this broad view, all of them fit together into one big package. I think that's basically all I wanted to tell you. So I'll conclude. We have proposed, based on physical reasoning, a new homological invariant for three manifolds with a double gradation. We have shown how this data refines and reduces to WRT invariance, and we actually checked it in a number of examples. I haven't told you, I just gave you a simplest one, but we have done it in cases, many more cases. And we have argued that there may be even a more richer, more extensive new homological invariant based on 1,060 theories, which we are currently developing, so that we'll see where that gets. Thank you. Well, I mean, in the cases of, for example, what we just said here, x times S1 you can view it as a yeah, that's right. X times S1 you can view it as four manifold, the boring one in that context. But if you want to have a Hilbert space, you need an extra S1. So you just divide your 6 into 1 plus something. So you can then decide what you can do or cannot do. So if you want a Hilbert space. Otherwise, if you want a number, then that's a different story. Which singular curves are we talking about? I'm not sure I'm familiar with what you're saying.
Singular complex curve in plane, and there was a result between Blaschelli and Oblomov that the Hilbert points on this.
Oh yeah, you mean the relation to that? We explored that problem later on. Yes.
Did you do it for WRT variance? So let's say I give you a complex surface with AD singularity, and I look at the Hilbert points on the complex surface intersected with S5.
No, I don't think that has been studied. At least I haven't studied. I don't know if it's been studied in the math literature. We haven't studied it. I haven't studied it, so I better not guess what it is. Either so. That's a very good question. Naively, you would think it's very unnatural mathematically. You have a manifold, you have a group, so you should take all. If you take anything flat, you should take all flat. Why abelian flat? Well, first of all, it seems to be the case. I don't have a deep explanation other than that fact. But there are 2 or 3 reasons why we think it's not unnatural. First of all, these things seem to label charged states. Charges are abelian. Charges you add in the physics context. It's like homology. If you have a non-abelian stuff, your abelianization of this is what appears as charges. So that's one picture. Secondly, in the study of these partition functions in the resurgence program, it turns out these abelian ones again play a key role, even though you're trying to talk about the full answer. It seems the abelian parts play the key role. So it seems like for some reason abelian ones are playing a more role than they deserve. But I do not have a deep, I wish I could tell you a much simpler explanation. I don't have it. And that was one of our surprises. That was one of the hardest things to solve for ourselves. But I would say that, sorry? Okay, but I would say that one thing I want to point out is that here we want to make contact with WRT, but you didn't have to, in which case it's much neater. Namely, forget about flat connection or anything. An X manifold, just put on S2, gives you a Hilbert space. The X times S2, three-manifold times S2 gives you a Hilbert space, and you study that. That does not need, and because it has no boundaries. The reason we had the flat connection or anything like that was because cigar has a boundary. You have to study what happens asymptotically. You have choices. That's not a very natural way to do. If you want to make contact with Chern-Simons, you have to do that. But maybe you're interested in something a little neater without boundary data and so on. Yeah, you could have done irreducible flat connections, arbitrary one, but we are saying that somehow we are interested in abelian ones at the end.
Which version of the cyberwing or homology is
Which one connects to you? I'm not an expert on that part, but U1/1, what is the? Is it known? I think one of them is known as connected to U1/1, correct? The Chern-Simons theory on U1/1. The one that connects to U1/1 Chern-Simons theory? We can talk about it maybe.